Today we are going to dive into generative AI, specifically aiming to focus on natural language processing. This session assumes that you have learned everything in recurrent neural network in previous sessions. Please review those sessions if you feel like you forgot about them. With that being said, let's get started. In this session, we will describe and demystify the relevant artifacts in the paper, Attention is All You Need by Vaswani and their team in 2017. This paper was a great advance in the use of the attention mechanism, being the main improvement for a model called transformer. The most famous current models that are emerging in NLP tasks consist of dozens of transformers or some of their variants, for example, GPT-2 or BERT. We will describe the components of this model, analyze their operation and build a simple model that we will apply to a small-scale NMT problem, neural machine translation. Why do we need transformer? In sequence-to-sequence problems such as the neural machine translation, the initial proposals were based on the use of RNNs in an encoder-decoder architecture. These architectures have a great limitation when working with long sequences. Their ability to retain information from the first elements was lost when new elements were incorporated into the sequence. In the encoder, the hidden state in every step is associated with a certain word in the input sentence, usually one of the most recent. Therefore, if the decoder only accesses the last hidden state of the decoder, it will lose relevant information about the first elements of the sequence. Then, to deal with this limitation, a new concept were introduced: the attention mechanism. Instead of paying attention to the last state of the encoder as is usually done with RNNs, in each step of the decoder we look at all the states of the encoder, being able to access information about all the elements of the input sequence. This is what attention does: it extracts information from the whole sequence, a weighted sum of all the past encoder states. This allows the decoder to assign greater weight or importance to a certain element of the input for each element of the output. Learning in every step to focus in the right element of the input to predict the next output element. But this approach continues to have an important limitation: each sequence must be treated one element at a time. Both the encoder and the decoder have to wait till the completion of T1 steps to process that Th step. So when dealing with huge corpus, it is very time-consuming and computationally inefficient. What is the transformer? In this work we propose the transformer, a model architecture eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significantly more parallelization. The transformer is the first transduction model relying entirely on self-attention to compute representations of its input and output without using sequence-aligned RNNs or convolution. What is self-attention? Self-attention is a process that operates on sequences of vectors. It takes an input sequence of vectors, x1, x2, xt, and produces an output sequence of vectors, y1, y2, yt. The vectors have a dimension of k. To compute the output vector e, self-attention calculates a weighted average of all the input vectors, typically using the dot product as the weighting mechanism. Every input vector is used in three different ways in the self-attention mechanism: the query, the key, and the value. In every role, it is compared to the other vectors to get its own output e, query, to get the jth output yj, key, and to compute each output vector once the weights have been established, value. To obtain this roles, we need three weight matrices of dimensions k, x, k, and compute three linear transformation for each 11. These three matrices are usually known as K, Q, and V, three learnable weight layers that are applied to the same encoded input. Consequently, as each of these three matrices come from the same input, we can apply the attention mechanism of the input vector with itself, a self-attention. These three matrices are usually known as K, Q, and V, three learnable weight layers that are applied to the same encoded input. Consequently, as each of these three matrices come from the same input, we can apply the attention mechanism of the input vector with itself, a self-attention. The input consists of queries and keys of dimension dk, and values of dimension dv. We compute the dot product of the query with all keys, divide each by the square root of dk, and apply a softmax function to obtain the weights on the values. Then we use the Q, K, and V matrices to calculate the attention scores. The scores measure how much focus to place on other places or words of the input sequence W.R.T a word at a certain position. That is, the dot product of the query vector with the key vector of the respective word we're scoring. So, for position 1 we calculate the dot product of Q1 and K1, then Q1, K2, Q1, K3, and so on. Next we apply the scaled factor to have more stable gradients. The softmax function cannot work properly with large values, resulting in vanishing the gradients and slowing down the learning, too. After softmaxing we multiply by the value matrix to keep the values of the words we want to focus on and minimizing or removing the values for the irrelevant words. Its value in V matrix should be very small. In the previous description the attention scores are focused on the whole sentence at a time. This would produce the same results even if two sentences contain the same words in a different order. Instead, we would like to attend to different segments of the words. We can give the self-attention greater power of discrimination by combining several self-attention heads, dividing the word's vectors into a fixed number, h, number of heads, of chunks, and then self-attention is applied on the corresponding chunks, using Q, K, and V submatrices, according to Peter Blohm, transformers from scratch. This produces h different output matrices of scores. But the next layer, the feed-forward layer, is expecting just one matrix, a vector for each word, so after calculating the dot product of every head, we concatenate the output matrices and multiply them by an additional weights matrix WO. This final matrix captures information from all the attention heads. We mentioned briefly that the order of the words in the sentence is an issue to solve in this model, because the network and the self-attention mechanism is permutation invariant. If we shuffle up the words in the input sentence, we get the same solutions. We need to create a representation of the position of the word in the sentence and add it to the word embedding. To this end, we add positional encodings to the input embeddings at the bottoms of the encoder and decoder stacks. The positional encodings have the same dimension as the embeddings, so that the two can be summed. There are many choices of positional encodings. Now, putting everything together, we have a transformer architecture. Encoder. The encoder is made up of several layers, typically 6 in this case. Each layer consists of two parts: a self-attention mechanism that helps the model understand the context of each word in the input sequence, and a feed-forward network that processes the information further. To make it easier for the model to learn and remember information, connections are made around these parts, and the output is normalized. The dimensions of the outputs are typically 512. Decoder. The decoder also has several layers, usually 6, just like the encoder. In addition to the self-attention and feed-forward parts found in the encoder layers, the decoder adds a third part. This part helps the decoder pay attention to relevant information from the encoder. Similar to the encoder, connections are made around these parts, and the output is normalized. The self-attention in the decoder is slightly modified to prevent it from looking ahead in the sequence. This, along with shifting the output by one position, ensures the model generates accurate and coherent output. How does a transformer leverage multi-head attention? The transformer model uses multi-head attention in 3 different ways. 1. Encoder-decoder attention. In this type of attention, each position in the decoder pays attention to all positions in the input sequence. The queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. This allows the decoder to gather information from the entire input sequence, similar to how traditional sequence-to-sequence models work. 2. Encoder self-attention. The encoder also has self-attention layers. In these layers, all the keys, values, and queries come from the same place, which is the output of the previous layer in the encoder. This means that each position in the encoder can look at and gather information from all the positions in the previous layer of the encoder. 3. Decoder self-attention. Similarly, the decoder has self-attention layers where each position in the decoder can attend to all positions in the decoder up to and including that position. However, to preserve the order of information flow and ensure the model generates output in a sequential manner, we need to prevent the decoder from looking ahead. This is done by masking out, setting to -infinity, certain connections in the attention mechanism, ensuring that each position can only attend to positions that came before it. Overall, the multi-head attention mechanism in the transformer model enables the model to selectively focus on different parts of the input and generate contextually rich representations, improving its ability to understand and generate coherent output. In the English to German translation task, the big transformer model, transformer, big, performed better than any previously reported models. We use BLEU score to measure the performance. BLEU, Bilingual Evaluation Understudy, score is a metric used to measure the quality of machine-generated translations by comparing them to human-generated translations. It evaluates how well a machine translation system aligns with reference translations provided by humans. Think of it like a grading system for translations. The BLEU score ranges from 0 to 100, with a higher score indicating better translation quality. A score of 100 means the machine translation is nearly identical to a human translation. To calculate the BLEU score, the machine translation is compared to one or more reference translations. The score considers how many words or phrases in the machine translation match the reference translations. It also looks at the length of the translation and penalizes overly long or short translations. In simpler terms, the BLEU score tells us how close a machine translation is to a human translation. Higher scores mean better translations, while lower scores indicate more room for improvement. It helps researchers and developers assess and compare the performance of different translation models and techniques. The natural language translation machine achieved a new state-of-the-art score called BLEU of 28.4, surpassing the previous best models by more than 2.0 BLEU. This model was trained for 3.5 days using 8 GPUs. Even the base model of the transformer outperformed all published models while requiring less training time. Similarly, on the English to French translation task, the big transformer model achieved a BLEU score of 41.0, surpassing all previously published single models. Notably, it achieved this score at less than 1/4 the training cost of the previous state-of-the-art model. In this case, the dropout rate used was different from the English to German model. To obtain the base models, the last 5 checkpoints were averaged, while for the big models, the last 20 checkpoints were averaged. During translation, a beam search with a beam size of 4 and a length penalty was used. These specific hyperparameters were chosen after experimenting with the development set. The maximum output length was set to the input length plus 50, but the translation process could terminate earlier if possible.